Okay, let us start the last session of this conference. To start this last session, I would like, first of all, to congratulate our guests from France and of French origin of national holiday. And now I'm passing, to the first talk in this session, Parfrey. 25 minutes, including questions.
Okay, thanks. All right, so I'll be talking about the interactions between magnetized rotating neutron stars and accretion flows. And I'll primarily be talking about interactions with millisecond pulsars. So we heard a lot about these today in various flavors that they come in. Primarily the accretion-powered sources, which accrete via these magnetically funneled accretion channels. We'll be hearing more about the nuclear-powered sources, which are observable through their X-ray bursts in the next talk from Yuri. And then we also heard this morning from Alessandro about these very interesting transitional systems, which we see in more than one state, so the X-ray pulsar state and the radio pulsar state. And because we see them in the two very different manifestations, hopefully we can learn different things from each state and learn more about both these systems and all the other accreting millisecond pulsars in general. So these systems pose many observational puzzles for theorists to explain. So one is changing pulsar spin frequencies over fairly short time scales. So this is not only the first example of this phenomenon, but the first accretion-powered X-ray pulsar ever discovered, SEN-X3, showing quite large changes in spin period over a timescale of hours. And this is seen in more or less all accreting pulsars, including the millisecond pulsars. So secondly, the millisecond pulsar spin frequency distribution is very strange. So we see this kind of fairly abrupt cutoff where it's kind of somewhat uniform up to some cutoff frequency, and then you just don't see any more objects, even though the instrumental response would tell you that you can easily detect these sources up to a spin frequency for this instrument RXE up to about 2 kilohertz. The breakup frequency for these stars should be around 1200 hertz around here. So there's no particularly good reason why we shouldn't be able to detect things in here. And explaining why this abrupt cutoff is where it is very hard to do. So many things have been proposed, including kind of fairly basic magnetosphere disk interaction, which is the kind of thing I'll be talking about here, but also more exotic things like gravitational radiation. And then finally, jets from neutron stars. So this is something we haven't actually heard about all that much in this conference, but neutron stars do produce jets just like black holes. So for example, SCO-X1 here was discovered in 1981 to have this sort of morphology that looks a lot like an extragalactic radio source or a radio galaxy. You have a central radio core and these two lobe-like things here. And it was later shown to have these kind of slow ballistic ejections from the central core. And you can also see rapid flares in the X-rays, and you can see a flare from the core and a flare from things further out. And you can estimate what kind of energy transfer speed you would need to have to transfer energy from the core to these outer parts, assuming that the two are linked. And you end up with quite a large Lorentz factor, greater than 3. So it's a very relativistic jet. And then SIR-X1, another one of these Z sources, has been shown to have an even larger Lorentz factor, greater than 15. So not only do neutron stars make jets, they make very relativistic jets. And this is not just a few sources. This is basically almost all classes of accreting neutron stars make things that, even if they're not resolved, look very much like the kind of continuum radio jets that you see from black hole binaries. So yeah, you have all of your favorites, the accreting millisecond pulsars, the atolls, and the Z sources up here. And one thing that's interesting here is that it looks like the accreting millisecond pulsars are lying slightly harder in the radio at the same X-ray than some of the other sources, possibly indicating that maybe stellar rotation has got something to do with this. Okay, and then finally, so the ULX pulsars that Yuri talked about are rotating much more slowly, but they are also very interesting sources in their own right, and hopefully I'll be able to get to something related to them near the end of the talk. Okay, so the main thing I'll be focusing on is the global magnetospheric geometry. So basically, is the global magnetosphere mostly closed, so you have more or less dipolar field lines connecting the star to the disk, like in the Gaussian-Lamb model, or is it somewhat open? So you have these field lines which have been opened by differential rotation and magnetic pressure to large radii. And this is important because if you have magnetic coupling between the star and the disk, the two can exert torques on one another, and they can exchange energy and angular momentum. And also because if you have these open field lines, you can drive a radio jet from the star. So simulations have been done on these and related systems like protostars for a long time. So for example, all the way going back to the mid-90s, people have seen things like these kind of magnetic field opening events, reconnection, flares, these kind of funnel flows that we would expect to have, and they've measured the accretion torque. And also people have found the kind of axial magnetized jet. So this is basically a magnetic tower that is being launched upwards by these torsional alpha waves. But one thing that has not been done by these groups is relativistic simulations. And this is interesting because in the relativistic case, the magnetic field itself conveys inertia, and therefore that there's kind of a minimum torque per field line that can be applied by an open field line, which is given just by the inertia of the electromagnetic field itself. So looking at some of these magnetospheres in a relativistic simulation, so here's an example for a fairly thin disk. Initially, you start with a dipole. You set both the disk rotating in a Keplerian way, the star rotating. The light cylinder for the star is out here, this kind of thin line that you can barely see. And basically what happens is you have flux opening due to generation of toroidal magnetic field. B phi squared gives you magnetic pressure, pushes everything open. You form current sheets which then reconnect, giving you these kind of nice reconnecting current sheets here, and ejection of these large plasmoids. And this kind of continues, but the most important thing is that what happens is a lot of the magnetic field is open. So you have very little flux that's connecting the star to the disk. This can also be done for thick disks, and even though you would not expect this to necessarily be as efficient in that case, you still find that you get quite a lot of magnetic field opening in the thick disk case. So what's happening here is that you're basically solving Maxwell's equations everywhere, but what you have above the disk is relativistic force field electrodynamics, and inside the disk, you're basically applying a certain current density, saying that you know what the velocity field of the disk should be, Keplerian rotation and some radial hillfall. So this is kind of a simplified system where you're using the force-free system, which is basically MHD with the magnetic field turned all the way up to be super dominant in the magnetosphere. And in the kind of disk region, you're just saying, I'm going to make a kinematic approximation because I know what it's doing. So what you find is this is kind of a grid of very simplified models in which I even turned off the accretion rate because the accretion speed because it was so small. And I set a constant conductivity in the disk. And this conductivity is the kind of turbulent, effective diffusivity you would expect from the MRI. So the idea was to look at how much magnetic flux from the star is open compared to the amount of open flux you would expect in the isolated state just from the rotation of the star alone. So the idea is you start marching your disk inwards from the light cylinder out here, inwards and inwards and inwards until it crosses co-rotation, and you measure in each case how much magnetic flux is open to infinity or to some large radius. And you find that it increases very rapidly. And if you make kind of a very simple model by saying, well, this is all kind of closed magnetic flux inside the light cylinder, it's going to more or less look like a dipole. I know how a dipole magnetic field behaves. It goes like, flux function goes like 1 over r. I can make this very simple approximation with this dashed line. And it kind of traces what the simulation does pretty well. You can do a better job by using an isolated pulsar simulation with this dashed red line. But what it tells you is that the amount of flux opening is pretty large. The efficiency of doing that is high. And also, if you look kind of equivalently at the torque applied by these open magnetic field lines to the star, it also goes along pretty well with kind of simple models that you could make just by approximating, say, a dipole field for the closed zone. So you can make a toy model and say, well, I'm going to approximate all the spin down torque and jet power is coming from these open field lines. I know roughly what that should do because I can say it's somewhat similar to a dipole. I know what an isolated pulsar looks like. I know the spin down power just goes like mu squared. This is the magnetic moment squared times rotation rate to the 4, or simply just like a rotation rate squared times the open magnetic flux. I'm opening more magnetic flux. This number goes up. And then the spin down power, or equivalently the torque, increases like the square of this. So by doing this, you can make a very simple model. You say, well, I know what an isolated pulsar does. I can make a simple model for how my magnetic flux is opened by interaction with the disk. Then I can say, well, the torque is just going to increase over its isolated pulsar value by the square of this with some efficiency factor zeta here, which we expect to be somewhat close to 1 if this is an efficient process. And then you can kind of put this together and say, well, if this is my only spin down contribution, and it only happens when this disk is inside the co-rotation radius, you can make a very simple model. Or, well, the spin down process happens when it's anywhere inside the light cylinder. You only have spin up from accretion onto the star by the usual amount when the disk gets inside the co-rotation radius. And you can come up with a very simple model for what you might expect the torque to be in this case. And one interesting thing you can do with this, you can say, well, if I want to have spin equilibrium, I just want to make these two things equal to one another, you just say, well, the spin up part is equal to the spin down part from this open flux. You rearrange it and you get an equilibrium spin frequency. And it actually looks somewhat similar to the kind of cutoff value that we saw earlier in the talk, so around 700 hertz. So one thing that's interesting is that so zeta here is the flux opening efficiency, this c is magnetospheric radius, this truncation radius divided by the classic alpha radius. If you put in, say, 0.6 for both zeta and c here, the prefactor here comes out to like 750, so it puts you right in the ballpark for these kind of parameters. Another interesting thing is that if you're in instantaneous spin equilibrium from this process, you can rearrange things such that magnetospheric radius divided by light cylinder radius, almost everything drops out. All that is left is these model parameters. And then you can say, well, if I want to see channeled accretion, I need to have my magnetospheric radius outside the star. And that actually just gives you a maximum spin for accretion-powered MSPs if they're in instantaneous spin equilibrium by this process. And if you look at these reasonable values of c, as we heard from Sergey this morning, this should be around 0.5 to 0.7 from observations. If flux opening efficiency is fairly large, 0.6, 0.8, it basically puts us in the ballpark here for giving this maximum spin frequency in and around the cutoff that's observed. Okay, if the open flux is collimated, you'll basically get something that looks like a relativistic jet, which is also easy to estimate. You can make the usual estimates. Say here I'm going to scale my m dot via the Eddington rate because I'm interested in explaining jets from these powerful sources like Z sources. And you get quite a lot of power. So if I have, say, SCOX1 or CRX1, where people have estimated that the jet power should be greater than 10 to the 35, by saying, let's take some fairly reasonable numbers here for these sources, and you can get a jet via this mechanism of a very similar magnitude. Okay, so that's all very well, but what you really want to do is do the problem more self-consistently and do the disk, basically evolve the disk so you're no longer making the kinematic approximation, the whole thing is evolving in a self-consistent way. So I'm next going to describe is a set of GR-MHD simulations that basically solve the whole thing in general relativity in a much more self-consistent way. So the idea is that you start with all of your accreting matter initially outside the light cylinder. You're going to do it in a fixed metric, the curve metric, with a kind of a fairly slow rotation that's appropriate for the star that you're interested in. And we want to have very high magnetization in the force-free or nearly force-free part of the magnetosphere outside of the disk stuff that's coming in. And that was the hard part of doing this, is keeping that highly force-free part well-behaved. So other important parts of the simulation is it's total energy conserving, so that means that you are including the effects of shock heating. And we have a relativistic gas equation of state, gamma equals 4/3, which means that this is roughly giving you what you would expect, say, for a ULX, where you have photon trapping and no radiation of energy out of it. Okay, so the equations we're solving are the equations of relativistic MHD. The important part here is that we have this B squared term inside our inertial term, right? So this is basically the non-relativistic limit. This is the half rho V squared, giving you this is the inertia. So now we have additional inertia from B squared here. So in the force-free stuff I was talking about earlier, you're basically saying this is much bigger than all of these other terms. But here we're going to keep all of the terms, including the inertial ones. I'm going to show the first simulation here. So we have the star. This is the light cylinder for the star once it starts rotating. Co-rotation radius is in here. This green line here is the last closed field line if the star is isolated. And then we're going to have all of our reservoir of stuff that can accrete out here, so at 3 light cylinder radii and further out. It's initially threaded by a magnetic field whose orientation is such that when it comes into the closed zone, the star and the disk field are anti-parallel, so they can reconnect with one another, and that'll become important. Here in this case, the stellar magnetic moment is 5 in units that the density of the pressure max is 1, so I'm going to be increasing this later on. I'm going to see what that does. So this is all our accreting stuff out here. This here is all our nearly force-free magnetosphere. So you set the thing rotating. You form basically something that looks like an isolated pulsar magnetosphere. This thing starts out in equilibrium but becomes unstable due to the MRI. Stuff starts to move inwards against the pulsar wind here. It starts to kind of push these field lines out of the way. gets closer and closer to the light cylinder and eventually crosses it. Then you can see it start to reconnect here, right? And that reconnection allows it to get in more easily. And also these field lines here near the poles are getting opened because they reconnect and are able to be lifted out. So what's happening is the reconnection is allowing this sort of jet which is forming here to have a larger open magnetic flux than it would otherwise. So this is basically the enhanced pulsar wind flux opening thing I was describing earlier. So what you find is this kind of accretion funnel down near the surface. It's inside the co-rotation radius. You get this kind of thick disk that you would expect from, say, a ULX. Okay, so that's what happens when you have anti-parallel magnetic fields. So let's look at, this is just a snapshot, so you can see mass density. This is toroidal magnetic field. So mostly at each pole, it's all coming in one direction. This is the kind of rotationally induced toroidal magnetic field that spins down the star. But you also have this one of the opposite side, which is very thin, and this is the, in this case, the accretion funnel. So this is the opposite, so this is pulling the star forwards and increasing its rotation rate. So this F thing here is part of how we do this force-free and MHD thing together. So this is a passive scalar that initially is only inside our reservoir of accreting gas. It gets brought in, and that allows us to do slightly different things in each of these two regions, allowing us to get very high magnetization in the force-free region. So you can see down by the star here, our magnetization, so magnetic energy density divided by rest mass energy density, is greater than 10 to the 4 near the star. And this allows you to do very clean comparison between the accreting and non-accreting states. Okay, so if instead of having anti-parallel fields in the star and disk, now they're parallel, and so you see something very different. And again, these are 2D simulations, and that's going to become important later. So you have parallel magnetic fields, so they can't reconnect against one another. And what's happening then is it's just forcing the stellar magnetic field down. And in fact, not only are you not increasing the amount of open flux, you're actually reducing it. There's additional field lines out here that were open that are no longer open. So that means that you might think, okay, maybe my jet mechanism isn't very robust because it's not opening fields in this case where you have some kind of large-scale field that's coming in that's of the wrong orientation. Okay, but let's leave that for now and come back to it later. So let's go back to our anti-parallel fields and just increase our stellar magnetic moment by a factor of 4 over what it was before. You set it running, and everything is kind of kept outside the co-rotation radius. Things kind of leak through every now and then, but more or less, accretion has been shut off, and you're in something that's somewhat close to the classic propeller state. It's outside the co-rotation radius, it's inside the light cylinder. You have stuff being kicked out by the stellar rotation. What happens is you have stuff that's surrounded by magnetic fields. That magnetic field reconnects with the stellar magnetic field, then it's connected to the star, and the star is able to get rid of it by sliding it off centrifugally. So reconnection is very important in all of these processes. So now we have propeller. So what happens if you keep increasing magnetic field strength? Let's go up by a factor of 4 again, and by a factor of 8. So what happens now is that the stellar field is suddenly so strong that it can really start fighting against this incoming accretion flow. In this case, it's pushing it out. So what's going to happen here is that on the left-hand side, this stuff is eventually going to find its way through the light cylinder and kind of be in this kind of marginal state where it's just about in and out of the light cylinder. Whereas in this case, the stellar wind is basically winning, and the accretion flow is not able to get in. Every now and then, it manages to kind of force its way through the equator in a sort of almost like an interchange motion by pushing these magnetic fields out of the way. But even when it does so and is able to get inside the light cylinder, it's very quickly kicked out again. So this can give you some very rapid transitions between stuff being outside the light cylinder, inside the light cylinder, and back. Okay, so we get 4 states: crushed, channeled, propeller, and excluded from the light cylinder. So what's most important here is that, well, firstly, magnetospheric radius basically follows the same laws you'd expect mu to the 4/7 as the kind of simple estimates. Secondly, that you, at least in the anti-parallel case, open up a lot of magnetic field, which gives you a jet power that scales very similarly to the simple model I described earlier. Okay, so in a kind of trying to show you some kind of preliminary stuff, 3D is important because you want to have a more realistic MRI dynamo, and because you want to be able to see the interchange instability of stuff as it tries to fight its way through the closed zone, the poloidal field that you find near the star. So this is a 3D simulation. So on the left hand, so what I've done is I've taken away parts of the sphere so you can see what's going on. So you have 2 vertical surfaces on each side and 1 horizontal surface. And then the left-hand side is going to be colored with toroidal magnetic field, the right-hand side with mass density, and the star is colored with mass density. So you set the thing going, and you'll see that. Why is this not going? That is strange. Okay, so what you should see is this stuff start to become unstable and flow in towards the star. But my computer has become unhappy with this situation. So we're going to skip that movie, unfortunately, and show you what happens here. Okay, so stuff becomes unstable, starts to spiral inwards, gets truncated by the star's magnetosphere, and then you eventually forms these accretion funnels here. But every now and then stuff is able to fight its way through in these kind of interchange modes, and you see these tongues in the equatorial plane here. So it shows you that you can have fairly stable accretion funnels at the same time as you have a certain amount of accretion into the equator. So this is just a 3D rendering of the field lines. So most of the field lines in the last simulation were mostly open, but the ones that were closed, that are interacting with the disk, are twisted back much more because there's much more inertia on these field lines because there is mass density threading them. These ones only basically have the inertia of the electromagnetic field, so they all have more or less the same twist. Okay, and then the last point is that we talked earlier about how the sign of the magnetic field in the disk with respect to that in the star was very important for opening or not opening field lines in that 2D case. So what this says is that in 3D that doesn't really obtain, because you have this is the electromagnetic jet power. The anti-parallel case where they can reconnect is in blue, but in the parallel case where in 2D the jet was completely killed off, now it's basically just as strong and it opens up and starts up just as rapidly as in the anti-parallel case. And the reason this happens is because in 3D now you can have these non-axisymmetric motions that can turn the field over, so it twists around and then it can reconnect and open up, so that the jet mechanism and the open flux mechanism seems to be fairly robust in 3D. You can do the same thing for an oblique rotator, but I think I'm running low on time, so I will go straight to my summary. And yes, okay. So in summary, we did some GRMHD simulations of accretion onto magnetized stars. We found the kind of 4 regimes you'd expect. In general, we find fairly efficient flux opening. And both the force-free and the MHD simulations support the kind of simple model I described earlier for the torques and the jets. And the 3D is important, but for some of the kind of broad qualitative parts, the orientation of the magnetic flux that's applied to the system doesn't appear to be that relevant. And I'll take questions.
Questions, please?
Yeah, so you didn't have any time to talk about oblique rotators. I was actually going to ask about orthogonal rotators. Can you briefly explain a little bit qualitatively what happens in those cases? Can you get away without opening as many field lines?
So I haven't looked directly at the orthogonal case yet. So the oblique case, so this is 45 degrees. And I think, so this is fairly preliminary. I think you still open a fair amount of field lines. You still form a jet. It's still, everything is fairly stable. You get these kind of 2 streams, so your accretion system isn't axisymmetric anymore. In the orthogonal case, I would expect to get less field line opening just from geometric principles, but I haven't been able to directly test that yet.
Okay, one other really quick question. So what are the timescales of these simulations? Like these tongues of material coming in, are these milliseconds per frame, or can you get minute timescales for these tongues of material coming onto the neutron star or not?
Yeah, I mean, I'm seeing this on very short timescales. So there were, I think, 6 frames per spin period. So okay. You're looking at, very short timescales.
Something comparable to the spin rate. Yeah, okay.
Okay, more questions? I don't see Arthur any.
There's one up there. In the right.
Okay, yeah.
Can you show me the slide where you had the numerical scheme of your code? It was the very first or second slide. I want to make sure if you have some physical prescription for resistivity.
Yeah, right. So that's way back here. Okay. This guy here. Yeah, so there's This is kind of a modification of the force-free system where I added some causal hyperbolic resistivity term to drive the system towards having a dissipative electric field along the magnetic field. So it dissipates alpha waves, but it doesn't dissipate fast waves.
Okay.
More questions? No? Let's thank the speaker again.